Hello, my name is Nahil Tariq. I want to introduce you to the 2024 Data Plus portion of the Mistral project. This project included myself and my teammates Bob Zhang and Manar Zain Al-Din. The project is funded by the National Science Foundation and Cisco. Our main objective was to develop an automated method for detecting anomalous or malicious network traffic. We broke this objective down into 3 steps: understanding a baseline of what normal traffic should look like, enriching our data by working with the red team to include synthetic attack data, and finally constructing an automated method based on our data and understanding. Now let's discuss our methodology over the course of this project and how we tackled our steps. As we start discussing step 1, we'll look at the structure of our Mistral pipeline. In the beginning, we focused our efforts on accessing data through Splunk. We used the Splunk search processing language to query large amounts of network traffic from our lab and try to establish trends that way. However, we quickly realized that we wanted to apply statistical methods to our data and that the access to live traffic data was overwhelming and not really helping us. So we decided to shift our focus to using static network logs. We manipulated those using Python, using NumPy and Pandas to perform exploratory data analysis and establish our baseline of what normal data is. The final part of step 1 was us removing anomalous sets of data that arose from the way data was stored from our lab or recorded. For example, we removed truncated data and over 10,000 entries of destination ports that were mis-ID'd as source ports. In step 2, we worked with the red team to simulate a port scanning attack, so we could have synthetic attack data to work with. We then performed an EDA on this new data set of normal traffic and simulated attack. In step 3, we set out to create a machine learning model that could best ID port scanning on our network. Some models we explored included a random forest model, support vector machine, and isolation forest. However, due to our limited synthetic data from only one simulated attack and our specific goal of IDing only port scanning, we mainly focused on the 2 techniques that Manar will detail now.
We create 2 types of machine learning model. The first one is logistic regression. It's designed to investigate data specifically for detecting port scanning activity in the network. Logistic regression is formulated model, which means it uses mathematical equation to describe the relationship between inputs and the output. And the model was trained on several features, including packet octet ratio, packet reverse packet ratio, number of connection, and destination port. And the model achieved 96% of accuracy. Our other model is neural network. It serves as a monitoring tool that analyzes data to predict port scanning activity. And this model was trained on features such as flow count ratio, similar to those used in the logistic regression model, flow duration, and destination port. And the neural network architecture enabled it to classify data more effectively. So it's achieved 99% of accuracy. And in addition, we experimented with several other models, including decision trees, random forest, support vector machine, and k-nearest neighbors. We choose to focus on logistic regression and neural network due to their excellent accuracy and ability to handle complex patterns in data.
Besides just looking at our model's test and training accuracies and having ROC curves and confusion matrices to look at, we tested our neural network model on a whole day's real traffic data of over 60,000 entries. And obviously on this day, there were no attacks, hence why in figure 4 in the confusion matrix for this test, you won't see any entries for the row 1. The model achieved a 79% accuracy, guessing false alarms only 21% of the time, which we decided was pretty decent.
We plotted the traffic patterns for flow count, octet count, and the PCR. These traffic visualizations help users to observe traffic fluctuations. In particular, the abnormal activities identified by the machine learning models are often associated with remarkable traffic spikes. We anticipate these direct visualizations of the network dynamics can cross-check with the results given by the machine learning models and can be easier for the users to comprehend. To sum up, by identifying abnormal activities through the use of machine learning, we have achieved over 96% accuracy for port scanning scenarios. We will develop more models for other types of abnormal events, such as storage malfunctioning. Traffic visualizations and other interactive features have been integrated with the web interface created by Code Plus team. You may find more details by scanning the QR code above. Finally, we convey our sincere gratitude to Duke IT Security Office staff, Chloe, Alex, and Eric, for their tremendous help along the way. We thank Code Plus and Honeypot's team for their cooperation and contributions. We also thank Data Plus management for their organization and making this project possible. Thank you very much.